There's a moon in our solar system where rain falls, rivers carve valleys, storms rage across continents, oceans stretch to distant horizons. Most people think weather requires water. That assumption shatters completely when you visit Titan. Tonight we're discovering how nature built a perfect weather machine using completely different ingredients. You'll see why this frozen moon became more Earth-like than any world we've found. Before we dive into this alien weather paradise, drop a comment about where you're listening from. If you enjoy these cosmic explorations, consider subscribing. These journeys to otherworldly phenomena are meant to be shared. For decades, scientists could only guess what happened on Titan's surface. Think orange clouds so thick you can't see through them. Nobody knew what lay beneath that hazy atmosphere. The mystery frustrated planetary scientists for generations. A robot spacecraft called Cassini changed everything in 2004. This probe traveled to Saturn and pierced through Titan's veil. What it captured redefined weather science completely. Rain was falling, actual droplets hitting the ground. But these weren't water, they were liquid methane, a gas we use for camping stoves. On Titan, it's cold enough that methane becomes liquid and falls like rain. The temperatures reach about 300 degrees below 0 Fahrenheit. That's colder than anywhere on Earth has ever been. In this alien deep freeze, methane behaves exactly like water does on our planet, forming clouds, falling as rain, and pooling into rivers. Titan's surface reveals something impossible. River networks that look exactly like Earth's Amazon basin. Meandering channels that could be the Mississippi Delta. Drainage patterns identical to every river system you've ever seen. These aren't carved by water, they're carved by liquid methane. The same stuff that heats your home when it's a gas. On Titan's frozen surface, this chemical stays liquid and flows like water through carefully sculpted channels. The largest rivers empty into seas spanning thousands of square miles. Scientists named the biggest one Kraken Mare. That's basically a methane ocean bigger than all the Great Lakes combined. It's filled entirely with liquid natural gas that would instantly freeze solid on Earth. The physics work identically with different ingredients. Erosion carves valleys, transport moves sediments, deposition builds deltas. The fundamental patterns don't require water. They just need any stable liquid under the right atmospheric conditions. Earth's water cycle powers all our weather. Water evaporates from oceans, forms clouds in the sky, falls as rain, flows back to the sea. This endless loop drives every storm and creates every river. Titan runs the identical process using methane instead of water. Solar heat evaporates methane from surface lakes. The methane vapor rises into Titan's thick atmosphere. It cools and condenses into droplets that form clouds. Those clouds eventually release methane precipitation that falls back to the surface. Some flows directly into rivers and lakes. Some seeps underground to form methane groundwater. Some get stored in polar regions during Titan's long seasons. This creates a complete weather system that mirrors Earth's hydrological cycle. The only difference is the working fluid. Methane instead of H2O. Nature proved that weather patterns don't depend on specific chemicals, just on having the right physics and temperatures. Titan's northern hemisphere contains something extraordinary. Vast bodies of liquid that stretch beyond the horizon. These aren't water oceans. They're seas filled entirely with methane and ethane, chemicals that exist as gases on Earth. The largest sea covers an area bigger than the Mediterranean. Scientists call it Kraken Mare, and it contains more liquid hydrocarbons than all of Earth's oil reserves combined. The liquid is so pure it's essentially rocket fuel floating on an alien world. These seas experience weather just like Earth's oceans. Waves crash against shorelines. Seasonal storms stir up the liquid surface. Tides might even occur due to Saturn's powerful gravitational pull on this distant moon. The hydrocarbon seas reveal how different chemistry can create familiar geography. coastlines with bays and peninsulas, deep basins and shallow regions, even what appear to be islands scattered across the methane seas. Titan functions like a massive chemical factory running continuously in space. The Moon's atmosphere contains nitrogen and methane that get broken apart by solar radiation. These fragments recombine into increasingly complex organic molecules. Lightning and cosmic rays provide energy for chemical reactions that create compounds far more sophisticated than simple methane. The atmosphere generates everything from ethane to complex hydrocarbons that scientists call tholins. That's the orange material that creates Titan's hazy appearance. These organic molecules rain down onto the surface constantly. Over millions of years, they've built up thick deposits of carbon-rich material. Some of these compounds are the same building blocks that led to life on Earth. The chemical processes never stop. Titan manufactures organic compounds at a rate that dwarfs any laboratory on Earth. This moon became nature's experiment in organic chemistry, creating molecules that might hold clues to how life began. Titan experiences seasons that make Earth's weather changes seem mild. Because Saturn takes 29 Earth years to orbit the Sun, each season on Titan lasts about 7 Earth years. That's longer than most people attend elementary school. These extended seasons create dramatic changes across the Moon's surface. During Titan's summer, methane evaporates rapidly from the southern hemisphere and gets transported through the atmosphere to the northern regions. During winter, the process reverses completely. Seasonal storms rage across the Moon during transition periods. These aren't gentle weather changes. They're massive atmospheric disturbances that can cover entire hemispheres. Imagine hurricanes that last for months and span areas larger than entire continents. The long seasons allow weather patterns to reach extremes impossible on Earth. Methane can accumulate in polar regions for years, creating vast seasonal caps. Then rapid seasonal changes redistribute this material across the entire Moon through atmospheric circulation. Titan's surface contains geography that would look familiar from space but alien up close. Sand dunes stretch for hundreds of miles, but they're made from organic particles instead of rock. Mountain ranges rise from the surface, but they're composed of water ice as hard as granite. Methane rainfall has carved river valleys that mirror Earth's Grand Canyon. Impact craters from ancient asteroid strikes dot the landscape, though Titan's thick atmosphere protects it from most space debris. The few craters that exist get gradually erased by ongoing erosion. Vast plains stretch across regions where organic sediments have accumulated over geological time. These flatlands contain the same drainage patterns you'd see on Earth. Networks of channels that collect methane runoff and direct it toward the polar seas. The landscape reveals a world shaped by familiar processes using alien materials. Erosion, deposition, and weathering operate according to the same physical laws that shape Earth, just with different starting ingredients and extreme cold temperatures. Titan raises profound questions about life in the universe. While the surface temperatures would instantly kill any Earth organism, some scientists wonder if different forms of life could exist in methane-based chemistry. Instead of water as a solvent, hypothetical life might use liquid methane. The Moon contains all the chemical ingredients necessary for complex organic processes. Carbon-rich molecules, energy sources from chemical reactions, stable liquid environments. The combination creates conditions that might support biochemistry completely different from anything we know. Future space missions plan to explore this possibility directly. NASA's Dragonfly mission will send a helicopter-like craft to Titan in the 2030s. This flying robot will search multiple locations for signs of chemical processes that might indicate life or its precursors. If life exists on Titan, it would prove that biology doesn't require Earth-like conditions. That discovery would revolutionize our understanding of where life might exist throughout the universe and expand our definition of habitable worlds beyond anything we currently imagine. You can't breathe Titan's atmosphere even though it's made mostly of nitrogen. That's the same gas that makes up 78% of Earth's air. Your lungs are designed to extract oxygen from air, but Titan's atmosphere contains almost no oxygen whatsoever. The atmosphere consists of 95% nitrogen gas. Earth's atmosphere is only 78% nitrogen. So Titan actually has a higher concentration of the gas that fills most of Earth's air. But breathing pure nitrogen kills you within minutes. Your body needs oxygen to survive, and Titan's air contains less than 1% oxygen. The remaining 5% is mostly methane, a gas that would make the air deadly for human lungs. This creates a deadly paradox where familiar chemistry becomes completely hostile to life. Titan's atmosphere proves that having the right building blocks doesn't guarantee habitability. You need them in exactly the right proportions. The atmospheric pressure on Titan's surface reaches 1.5 times Earth's sea level pressure. That means the air pushes down on every square inch with 50% more force than what you experience right now. This crushing pressure comes from Titan's incredibly thick atmosphere. The air extends much higher into space than Earth's atmosphere does. Imagine Earth's entire atmospheric blanket, then add another half atmosphere on top. Standing on Titan would feel like being submerged 15 feet underwater in a swimming pool. Your ears would pop constantly. Your breathing would require more effort. The dense air would make every movement slightly more difficult. Yet this extreme pressure creates the perfect conditions for liquid methane to exist on the surface. Without this atmospheric weight, Titan's methane would instantly boil away into space, and the moon would become a frozen, airless rock. Unlike Earth's greenhouse gases that include water vapor and carbon dioxide, Titan's warming comes almost entirely from methane. This gas makes up only 5% of the atmosphere, but it traps heat far more effectively than Earth's main greenhouse gases. Methane molecules absorb infrared radiation 25 times more efficiently than carbon dioxide. Even in small amounts, methane captures and holds heat that would otherwise escape to space. Without this greenhouse effect, Titan would be too cold for any liquid to exist on its surface. The methane greenhouse effect raises Titan's surface temperature by about 20 degrees Fahrenheit. That doesn't sound like much, but it's the difference between a completely frozen world and one where liquid methane can flow and evaporate. This demonstrates how powerful greenhouse gases can transform entire worlds. A small percentage of the right molecules can mean the difference between a dead rock and a dynamic world with weather rivers and seasonal changes. Titan's atmosphere contains a thick layer of orange haze that completely obscures the surface from space. This isn't pollution. It's organic molecules created when solar radiation breaks apart methane and nitrogen in the upper atmosphere. Ultraviolet light from the sun hits methane molecules and splits them apart. The fragments recombine with nitrogen to form complex organic compounds called tholins. These molecules absorb blue light and scatter orange light, giving Titan its distinctive amber appearance. The haze layer extends hundreds of miles above Titan's surface. It acts like a permanent fog bank that early telescopes couldn't penetrate. Scientists had to send spacecraft equipped with radar to map the surface hidden beneath this organic smog. This atmospheric chemistry factory continuously produces organic molecules that eventually rain down onto Titan's surface. Over millions of years, these compounds have built up thick deposits of carbon-rich material across the moon's landscape. What happens when you mix nitrogen and methane in the presence of solar radiation? You get a chemistry experiment that's been running continuously for billions of years. Titan's upper atmosphere functions like a massive laboratory manufacturing organic compounds. Solar ultraviolet radiation provides the energy to break chemical bonds. When methane and nitrogen molecules get shattered by this energy, their pieces recombine in increasingly complex ways. Simple two-atom molecules grow into chains containing dozens of atoms. The atmosphere produces everything from methane to acetylene to hydrogen cyanide. Some reactions create the same amino acid building blocks that led to life on Earth. All of this happens naturally in Titan's atmospheric chemistry lab. This process manufactures organic molecules faster than any laboratory on Earth could produce them. Titan became nature's proof that complex chemistry doesn't require life. Sometimes the right atmospheric conditions can build sophisticated molecules all by themselves. Titan's methane lakes don't just sit there like pools of gasoline. Solar energy constantly heats their surfaces. You can watch liquid methane molecules break free from the surface tension and float upward as invisible gas. This evaporation process works identically to water evaporation on Earth. Heat from the sun provides energy that transforms liquid methane into methane vapor. The warmer the surface temperature, the faster liquid methane escapes into Titan's atmosphere as gas. The evaporating methane carries tremendous amounts of energy with it. When liquid changes to gas, it absorbs heat from the surroundings. This cooling effect helps regulate Titan's surface temperatures around the methane lakes. Solar-powered evaporation creates the foundation for everything else in Titan's weather system. Without constant evaporation from surface lakes, there would be no methane vapor in the atmosphere, no clouds, no rain, and no weather at all. Rising methane vapor encounters an atmosphere far denser than anything on Earth. Titan's atmospheric pressure reaches 1.5 times Earth's surface pressure. That creates completely different behavior for rising gas compared to Earth's thin air. The dense atmosphere slows down convection currents that carry methane vapor upward. On Earth, water vapor can rise rapidly through relatively thin air. On Titan, methane vapor must push through much thicker atmospheric layers. This slower convection creates more stable cloud systems that can persist for longer periods. Methane vapor doesn't just shoot up and immediately condense like water vapor does on Earth during summer thunderstorms. Dense atmospheric conditions allow Titan's methane vapor to mix more thoroughly before condensing. This mixing creates more uniform cloud coverage across large areas rather than the patchy, rapidly changing clouds common in Earth's thinner atmosphere. Earth's clouds form chaotically and unpredictably because water vapor condenses at wildly different temperatures depending on altitude and pressure. Titan's methane clouds follow much more organized patterns because methane condenses at consistent temperatures in the stable atmospheric layers. Methane vapor condenses when atmospheric temperatures drop to around 200 degrees below 0 Fahrenheit. Unlike Earth's water vapor that can condense at temperatures ranging from 32 degrees to well below freezing, methane has a much narrower condensation range. This consistent condensation temperature creates predictable cloud formation patterns. Methane clouds tend to form at specific atmospheric heights where temperatures reliably reach the condensation point. Earth's clouds can form at almost any altitude depending on local conditions. Organized cloud patterns make Titan's weather more systematic and less random than Earth's weather. The consistent physics of methane condensation creates weather systems that follow predictable rules, rather than Earth's chaotic atmospheric behavior. Once methane precipitation reaches Titan's surface, it behaves exactly like water in terms of erosion and transport. The liquid flows downhill under gravity's influence. It carves channels through surface materials. It carries sediments from higher elevations to lower areas. Methane runoff creates the same geological processes that shape Earth's landscapes. Surface erosion cuts valleys. Stream transport moves particles. Deposition builds up sedimentary layers in low-lying areas where methane rivers slow down and drop their loads. Some methane precipitation infiltrates below the surface, just like groundwater on Earth. This underground methane can emerge as springs in other locations. It can form underground reservoirs that feed surface lakes during dry periods. The dual behavior of surface runoff and underground infiltration creates complex hydrological systems. Titan proves that familiar geological processes don't require water. They just need any liquid that flows under the influence of gravity and atmospheric pressure. Seasonal methane transport on Titan operates on scales that make Earth's weather systems look tiny. Because Saturn takes 29 Earth years to orbit the Sun, Titan's seasons last about 7 Earth years each. That gives atmospheric circulation enough time to move methane across vast distances. During Titan's long summer seasons, methane evaporates preferentially from the heated hemisphere and gets transported through the atmosphere to cooler regions. This creates a massive atmospheric conveyor belt that redistributes liquid methane across the entire moon. The scale of this transport dwarfs anything that happens on Earth. Imagine if Earth's Amazon River could flow through the atmosphere for 7 years straight, carrying water from South America to the Arctic. That's the scale of methane transport that occurs during Titan's extended seasons. Long seasonal cycles allow weather patterns to reach equilibrium states impossible on Earth. Methane has enough time to redistribute completely before the next seasonal change reverses the atmospheric circulation patterns and starts the transport process in the opposite direction. Titan's polar regions contain methane lakes that function like enormous chemical batteries. These bodies of liquid methane store most amounts of material during winter seasons and release it back to the atmosphere during summer warming periods. The largest polar lakes contain more liquid hydrocarbons than all of Earth's oil reserves combined. Kraken Mare alone contains an immense amount of chemical energy. These reservoirs represent some of the largest concentrations of chemical energy in the solar system outside of gas giant planets. Seasonal storage and release cycles create long-term climate stability on Titan. When one hemisphere experiences summer and loses methane to evaporation, the opposite hemisphere's polar lakes gain that methane as seasonal precipitation. The system maintains balance over long time periods. This planetary-scale chemical battery system demonstrates how large methane reservoirs can regulate climate over geological time scales. The polar lakes help prevent Titan from losing its atmosphere to space by providing vast storage capacity that buffers against atmospheric loss. The methane cycle doesn't just move liquid around. It actively creates new chemical compounds through atmospheric reactions. As methane vapor circulates through Titan's atmosphere, solar radiation breaks apart some molecules and recombines them into more complex organic chemicals. Simple methane molecules get transformed into ethane, propane, and other hydrocarbons during their journey through the atmospheric cycle. These chemical reactions occur continuously as methane circulates between the surface and the upper atmosphere where solar radiation is strongest. The newly created organic compounds eventually condense and fall back to the surface as precipitation. This means Titan's rain contains a mixture of pure methane plus complex organic molecules that were manufactured during atmospheric circulation. Chemical transformation during circulation creates a system where weather actively builds organic chemistry. Unlike Earth's water cycle that simply moves H2O around, Titan's methane cycle functions as a planetary chemical factory that continuously manufactures increasingly complex organic compounds. Latent heat exchange during methane phase changes creates powerful climate regulation mechanisms on Titan. When liquid methane evaporates, it absorbs energy from the surroundings. When methane vapor condenses, it releases that same energy back to the environment. This energy exchange system buffers as against rapid temperature changes across Titan's surface. Areas experiencing high evaporation rates get cooled by the energy absorption process. Areas where methane condenses and precipitates receive warming from the energy release process. The enormous scale of Titan's methane reservoirs means the latent heat exchange system can absorb or release climate-regulating amounts of energy. This prevents runaway greenhouse effects or runaway cooling that could destabilize the entire atmospheric system. Energy balance through phase changes demonstrates how the methane cycle creates climate stability on planetary scales. The system self-regulates by automatically transferring heat from warmer regions to cooler regions through evaporation, transport, and condensation processes. Kraken Mare stretches across Titan's northern polar region like a massive liquid natural gas reservoir. This isn't water, it's an ocean of methane and ethane covering an immense area. You could sail across it for days and never see the opposite shore. The sea contains an enormous amount of liquid hydrocarbons. Imagine every gas station, every oil field, every petroleum product on our planet. Kraken Mare holds a vast hydrocarbon reservoir on a scale we do not see on Earth. This liquid stays stable because Titan's extreme cold keeps methane and ethane in liquid form. The temperature reaches 300 degrees below 0 Fahrenheit. At those temperatures, chemicals that exist as gases on Earth become thick liquids. Kraken Mare proves that vast oceans don't require water. The right combination of temperature and atmospheric pressure can create stable liquid bodies using completely different chemistry than anything we see on Earth. Ligeia Mare displays remarkably complex coastlines. The sea contains hundreds of bays, inlets, and peninsulas that create intricate geographical patterns. Some coastal features stretch for dozens of miles in serpentine curves. Scientists discovered these coastal complexities using radar that penetrates through Titan's thick atmospheric haze. The radar revealed shoreline details that rival Earth's most complicated coastlines, fjord-like inlets cut deep into the surrounding terrain. The complex coastlines form through erosion processes similar to those that shape Earth's seas. Liquid methane creates waves that constantly erode shoreline materials. Seasonal changes cause sea levels to rise and fall, carving different erosion patterns at various heights. Ligeia Mare demonstrates that familiar coastal geography emerges from universal physical processes. Erosion, deposition, and weathering create similar landscape patterns regardless of whether the liquid is water or liquid methane. Different lakes across Titan's surface contain dramatically different chemical compositions. Some lakes hold almost pure methane, the same gas used in camping stoves. Other lakes contain complex mixtures of ethane, propane, and heavier hydrocarbon molecules. Punga Mare contains methane-rich liquid. Scientists think this small but deep lake gets fed by underground springs of methane that bubble up from below the surface. The chemical purity suggests limited mixing with other compounds. Other lakes receive input from atmospheric precipitation that contains mixed hydrocarbons. When methane vapor travels through Titan's atmosphere, it undergoes chemical reactions that create ethane and other compounds. This chemically modified precipitation creates lakes with complex compositions. The chemical diversity proves that Titan's lakes don't just passively collect precipitation. They actively participate in chemical processes that separate, concentrate, and modify different hydrocarbon compounds across the Moon's surface. Does liquid methane create waves like Earth's oceans do? Absolutely. Titan's dense atmosphere generates winds that create surface waves across the hydrocarbon seas. These waves crash against shorelines with enough energy to erode solid materials and transport sediments. The waves behave much like ocean waves on Earth despite being made of completely different liquid. They build up height as wind energy transfers to the methane surface. They break against shorelines and dissipate their energy through erosion and sediment transport. Seasonal wind patterns create different wave conditions throughout Titan's long year. During storm seasons, larger waves form that can reshape coastlines more dramatically. During calm periods, smaller waves perform gentler erosion processes. Wave action proves that familiar ocean dynamics operate with any liquid under the right atmospheric conditions. The physics of wave formation, propagation, and coastal erosion don't depend on water. They depend on having liquid sources exposed to atmospheric winds. How deep are Titan's methane lakes? Some of the larger ones reach depths of several hundred meters. That's deeper than many Earth lakes and contains staggering volumes of liquid hydrocarbons. The deepest parts could submerge a 50-story skyscraper. Krakenmeer reaches maximum depths approaching 200 meters in some areas. The total volume of liquid in just this one sea is immense. The scale dwarfs any liquid hydrocarbon reservoir on our planet. Deep lakes maintain stable temperatures and chemical compositions compared to shallow bodies that experience more seasonal variation. The deeper liquid layers remain insulated from atmospheric temperature changes and wind-driven mixing. These massive hydrocarbon reservoirs demonstrate the scale of Titan's methane cycle. The lakes function as enormous storage tanks that regulate atmospheric methane concentrations and provide stability to the Moon's entire weather system. What happens when Titan's hydrocarbon lakes get cold enough to freeze? They create icebergs made of frozen methane and ethane that float on the liquid surface. These organic icebergs behave much like water ice on Earth's polar oceans. During Titan's 7-year winter seasons, some shallow areas freeze solid while deeper liquid remains unfrozen. The frozen sections break apart and float as methane icebergs across the liquid portions of the lakes. Wind and currents move these organic ice chunks around the sea surfaces. Hydrocarbon ice floats because frozen methane and ethane are less dense than their liquid forms. This creates the same floating ice dynamics that occur with water ice on Earth. Icebergs stay partially submerged with most of their mass hidden below the surface. Organic icebergs prove that freezing and melting cycles operate with any liquid that can solidify. The phase transitions between solid and liquid hydrocarbons create ice dynamics similar to those in Earth's polar regions despite completely different chemistry. Titan's lakes don't exist in isolation. They're connected by underground networks of liquid methane that function like groundwater systems on Earth. These subsurface hydrocarbon aquifers allow methane to flow between distant surface lakes through underground channels. Some lakes show synchronized level changes that indicate underground connections. When one lake's level rises, connected lakes also rise. When one lake drains, others drop accordingly. This synchronized behavior reveals the hidden plumbing that links Titan's surface liquids. Underground methane can travel vast distances through porous subsurface materials. Some connections link lakes separated by hundreds of kilometers. The underground networks create a moon-spanning hydrocarbon circulation system that operates entirely below the surface. Subsurface connectivity means Titan's lakes function as components of a single integrated hydrological system. Changes in one part of the system eventually affect distant lakes through the underground network that connects them all. Lake evaporation on Titan creates local climate effects that influence weather patterns across entire regions. When methane evaporates from lake surfaces, it absorbs heat energy from the surroundings. This cooling effect creates temperature differences between lake areas and surrounding terrain. Temperature differences drive local wind patterns that circulate methane vapor from lake surfaces to surrounding areas. These winds create lake effect weather similar to how Earth's Great Lakes generate local snowstorms and temperature modifications. Evaporating methane sometimes condenses into fog banks that hover over lake surfaces or drift inland. These organic fog clouds can persist for extended periods and create local visibility conditions similar to Earth's coastal fog but made of methane vapor instead of water. Lake-generated weather demonstrates how large liquid bodies influence regional climate regardless of their chemical composition. The thermal effects of evaporation and condensation create local weather patterns, using universal physical principles that operate with any volatile liquid. Titan's lake surfaces function as active chemical reaction zones where simple methane molecules get transformed into more complex organic compounds. Solar radiation hitting the lake surfaces provides energy that drives chemical reactions between methane and dissolved nitrogen compounds. These surface reactions create ethane, propane, and other hydrocarbons that change the lake chemistry over time. What starts as pure methane gradually becomes a complex mixture of different organic molecules. The chemical evolution happens continuously as long as solar energy reaches the lake surfaces. Some reactions produce compounds that are heavier than methane and sink to lake bottoms. Other reactions create lighter compounds that evaporate back into the atmosphere. This chemical processing creates chemical gradients within the lakes from surface to depth. Surface chemistry proves that Titan's lakes actively participate in organic molecule synthesis. They don't just store hydrocarbons. They function as chemical reactors that continuously manufacture increasingly complex organic compounds. Why do most of Titan's large lakes cluster in the northern polar regions? This distribution creates a hemispheric chemical storage system that regulates atmospheric methane concentrations across the entire Moon. The polar concentration isn't random. It's the result of long-term atmospheric circulation patterns. Titan's atmospheric circulation transports methane from the summer hemisphere to the winter hemisphere over the course of the Moon's long seasons. The northern lakes serve as collection points where atmospherically transported methane gets stored as liquid for years at a time. This storage and release system helps prevent Titan from losing methane from the atmosphere over time. Without the polar lakes acting as reservoirs, Titan's methane cycle would look very different. The lake distribution demonstrates how surface geography can regulate planetary atmospheres. The northern hemisphere lakes function as a global stabilizer that helps maintain atmospheric stability across geological time scales. What happens when solar ultraviolet light hits methane molecules floating in Titan's upper atmosphere? The high-energy radiation breaks apart the chemical bonds that hold methane together. Individual carbon and hydrogen atoms get scattered like pieces of a broken puzzle. But these scattered pieces don't just float away. They immediately start recombining in new arrangements that create completely different molecules. Simple methane gets transformed into ethylene and acetylene, chemicals with carbon atoms linked together in ways that don't occur in simple methane. This photodissociation process, that's when light breaks apart molecules, happens continuously throughout Titan's atmosphere. Every day, solar radiation destroys billions of methane molecules and rebuilds them into more complex organic compounds. The process proves that space environments can function as enormous chemistry laboratories. Given the right starting materials and energy sources, even the vacuum of space becomes a place where complex organic chemistry spontaneously occurs. Can lightning in an alien atmosphere create the same chemicals that life requires on Earth? Absolutely. If lightning bolts tear through Titan's nitrogen-rich atmosphere, they provide enough energy to break apart nitrogen molecules that normally resist chemical reactions. Cosmic rays, those are high-energy particles from deep space, also bombard Titan's atmosphere continuously. These energetic particles hit nitrogen molecules with enough force to shatter their chemical bonds. The broken nitrogen fragments immediately react with hydrogen to form ammonia and hydrogen cyanide. These nitrogen-fixing reactions create the same kinds of compounds that early Earth's atmosphere produced before life began. Ammonia provides nitrogen that living organisms need to build proteins. Hydrogen cyanide contains the carbon-nitrogen bonds essential for amino acid formation. Titan's atmosphere demonstrates how violent energy sources can drive chemistry that leads toward biological compounds. Lightning and cosmic radiation function as nature's chemistry tools that forge life-essential molecules from simple starting materials. Simple 2-carbon molecules floating in Titan's atmosphere don't stay simple for long. They start linking together through polymerization reactions. That's when small molecules connect like chemical building blocks to form much larger structures. Ethylene molecules bond together to create long hydrocarbon chains containing dozens of carbon atoms. Acetylene molecules link up to form complex ring structures. Nitrogen-containing fragments attach to these growing chains to create nitrile compounds. Those are organic molecules that contain carbon-nitrogen bonds. The polymerization process builds molecules that rival the complexity of compounds found in living organisms. Some of these atmospheric polymers contain chemical structures similar to components found in Earth's amino acids and nucleotide bases. Atmospheric chemistry proves that complex organic synthesis doesn't require life. Given sufficient time and the right chemical conditions, simple molecules spontaneously organize themselves into increasingly sophisticated structures. Why does Titan appear orange from space? The color comes from massive quantities of brown organic particles suspended throughout the atmosphere. Scientists call these particles tholins. That's a term for complex organic polymers that form when methane and nitrogen react under energy bombardment. Tholins form when solar ultraviolet radiation and charged particles hit methane-nitrogen mixtures in Titan's upper atmosphere. The energy input drives chemical reactions that build increasingly complex molecules until they become large enough to scatter light and create visible particles. These brown organic particles accumulate continuously in Titan's atmosphere. They grow larger over time through additional chemical reactions that add more carbon and nitrogen atoms to their molecular structures. Eventually, they become heavy enough to fall toward the surface as organic precipitation. Tholin production demonstrates how atmospheric chemistry can manufacture complex organic matter on planetary scales. Titan's orange haze represents one of the largest ongoing organic synthesis experiments in the solar system. Titan's atmosphere functions like a multi-story chemical factory where each floor produces different organic compounds. At high altitudes where solar radiation is strongest, methane molecules get broken apart into simple fragments. At lower altitudes where radiation is weaker, different chemistry takes over. The stratosphere, that's the atmospheric layer about 50 kilometers above the surface, specializes in producing acetylene and hydrogen cyanide. These molecules form when intense ultraviolet light hits methane and nitrogen. The troposphere near the surface creates different compounds through lower energy reactions. Temperature differences between atmospheric layers also determine which reactions can occur. Higher altitudes stay colder and favor certain chemical pathways. Lower altitudes remain warmer and drive completely different organic synthesis routes. Layered atmospheric chemistry creates chemical diversity that no single environment laboratory could match. Titan's atmosphere produces dozens of different organic compounds simultaneously by hosting different reactions at different altitudes. What goes up must come down, including the organic molecules manufactured in Titan's upper atmosphere. Complex hydrocarbons and nitrogen compounds, created by atmospheric chemistry, eventually grow heavy enough to fall toward the surface under the influence of gravity. This organic precipitation has been accumulating on Titan's surface for billions of years. Some areas contain deposits several meters thick of organic-rich compounds that originated as simple methane in the atmosphere. The chemical snow creates layers like geological strata that record the history of atmospheric chemistry. Different regions receive different types of organic deposition depending on local atmospheric circulation patterns. Polar regions collect different compounds than equatorial areas. Wind patterns distribute atmospheric chemistry products across the surface in complex spatial patterns. Surface deposition transforms Titan into a repository of organic compounds that took billions of years to synthesize. The Moon's surface preserves a chemical library of atmospheric synthesis products spanning geological timescales. Titan's methane lakes don't just store hydrocarbons. They function as liquid-phase chemical reactors where dissolved organic compounds continue reacting with each other. The lakes contain hundreds of different dissolved chemicals that arrive through atmospheric deposition and surface runoff. Organic molecules dissolve in liquid methane just like salt dissolves in water. Once dissolved, these compounds can react with each other in ways that don't occur in the gas phase. Liquid methane serves as a solvent that brings different molecules into contact for chemical reactions. Some reactions produce heavier compounds that sink to lake bottoms. Other reactions create lighter compounds that evaporate back into the atmosphere. This creates chemical cycling between the surface lakes and atmospheric chemistry systems. Lake chemistry demonstrates how liquid environments expand the range of possible organic synthesis reactions. Titan's hydrocarbon lakes function as natural chemical laboratories that continue the atmospheric chemistry experiments in liquid phase. Temperature acts like a chemical thermostat that determines which reactions can occur across Titan's diverse surface environments. Warmer regions drive different organic chemistry than colder areas. Even small temperature differences can create different chemical outcomes. Higher temperatures speed up chemical reaction rates. Reactions that take longer to complete in colder regions can happen faster in warmer ones. Temperature also influences whether reactions favor simple molecules or more complex polymers. Cold temperatures favor the formation of stable, simple compounds. Warmer temperatures provide more energy for polymerization reactions that build larger organic molecules. This creates chemical zonation across Titan's surface based on temperature gradients. Temperature-controlled chemistry proves how physical conditions shape organic synthesis on planetary scales. Titan's temperature variations create natural chemical laboratories with different specializations distributed across the Moon's surface. Titan's surface materials don't just provide landing platforms for organic compounds. They actively participate in chemical reactions as catalysts. Water, ice, crystals, and mineral surfaces provide reactive sites where organic molecules can attach and undergo chemical transformations. Catalysis occurs when surface materials speed up chemical reactions without getting consumed in the process. Ice crystal surfaces bring organic molecules into close contact and provide energy that helps break and form chemical bonds. This creates reaction pathways that don't exist in pure liquid or gas phases. Different surface materials catalyze different types of organic reactions. Some mineral surfaces specialize in building carbon chains. Others excel at incorporating nitrogen atoms into organic structures. The diversity of surface materials creates a variety of catalytic environments. Surface catalysis expands Titan's organic chemistry beyond what atmospheric and liquid phase reactions alone could achieve. The Moon's solid surfaces function as specialized chemical tools that enable synthesis routes impossible in other environments. How does Titan's weather system affect organic chemistry distribution? The methane cycle acts like a planetary chemical sorting system that collects and concentrates organic compounds in specific geographical locations. Atmospheric circulation patterns determine where complex chemistry gets focused. Evaporation from methane lakes carries dissolved organic compounds back into the atmosphere. Wind patterns transport these chemicals across vast distances before depositing them in new locations. Some areas receive chemical inputs from multiple source regions and develop exceptional molecular diversity. Polar regions can accumulate especially high concentrations of complex organic compounds because atmospheric circulation patterns often converge there during seasonal transitions. These chemical hotspots contain molecular libraries that represent the combined output of Titan's entire atmospheric chemistry system. Chemical concentration through atmospheric transport creates conditions where organic molecules reach densities that enable reactions impossible in dilute environments. Titan's methane cycle transforms the Moon into a planetary-scale chemical concentration and purification system. Imagine experiencing the same season for your entire elementary school career. That's exactly what happens on Titan. Each season lasts about 7 Earth years because Saturn takes 29 Earth years to complete one full orbit around the Sun. This creates seasonal cycles that dwarf anything experienced on Earth. While Earth's seasons change 4 times per year, Titan experiences only 4 seasonal transitions during an entire human generation. Children could be born, attend school, and reach adolescence while experiencing only summer or only winter. The extreme seasonal length occurs because Titan orbits Saturn, and Saturn orbits very far from the Sun. The greater the distance from the Sun, the longer it takes to complete an orbit. Saturn's vast orbital distance creates seasonal timescales that stretch beyond human lifespans. Extended seasons allow weather patterns to reach equilibrium, states impossible on rapidly changing planets. Atmospheric systems have enough time to fully develop and redistribute materials across the entire Moon before the next seasonal shift reverses everything. Titan experiences sunlight variations that make Earth's seasonal differences seem mild. Because Saturn's axis tilts relative to its orbital plane, each hemisphere receives dramatically different amounts of solar energy depending on the season. The differences reach 400% between summer and winter extremes. During summer, one hemisphere stays tilted toward the Sun and receives constant daylight for years at a time. During winter, that same hemisphere tilts away from the Sun and experiences years of continuous darkness or extremely weak sunlight. These extreme daylight variations drive massive energy imbalances between Titan's hemispheres. The summer hemisphere receives 4 times more solar energy than the winter hemisphere. This creates temperature differences that power atmospheric circulation on scales impossible with Earth's gentle seasonal changes. Extreme solar energy differences prove how orbital mechanics can create climate conditions far more dramatic than anything experienced on planets with shorter orbital periods or smaller axial tilts. When seasons change on Titan, the entire global wind system reverses direction like a planetary-scale weather machine switching gears. Atmospheric circulation patterns that blew from north to south for 7 years suddenly reverse and blow from south to north for the next 7 years. This circulation reversal happens because atmospheric heating patterns completely flip when seasons change. The hemisphere that was cold becomes warm. The hemisphere that was warm becomes cold. Temperature gradients that drove north to south winds suddenly drive south to north winds instead. Global circulation reversal affects every aspect of weather system simultaneously. Storm patterns change direction. Precipitation patterns shift to new regions. Atmospheric pressure systems reorganize completely. The entire weather machine rebuilds itself with opposite circulation. Atmospheric reversal demonstrates how long-term seasonal changes can reorganize entire planetary weather systems. Earth's short seasons never allow such complete atmospheric reorganization to occur. How much methane moves between Titan's hemispheres during seasonal changes? Enough to fill millions of gasoline tanker trucks. The 7-year seasonal transitions create atmospheric transport systems that move methane on scales comparable to moving Earth's entire Mississippi River through the air. Atmospheric circulation carries evaporated methane from the summer hemisphere to the winter hemisphere, where it condenses and falls as precipitation. This creates one-way methane transport that continues for years until the next seasonal change reverses the flow direction. The scale of methane transport dwarfs any atmospheric transport system on Earth. Imagine Earth's water cycle operating in only one direction for 7 years straight, moving water from one hemisphere to the other without any reverse flow. That's the scale of Titan's seasonal methane migration. Massive atmospheric transport proves how extended seasons can create material redistribution impossible with Earth's rapid seasonal cycles. Long seasons provide enough time for complete hemisphere-to-hemisphere material transfer. Does Titan develop polar ice caps like Earth? Absolutely, but they're made of frozen methane and ethane instead of water ice. These hydrocarbon ice caps form when winter temperatures drop low enough to freeze methane directly from the atmosphere onto polar surfaces. Polar ice cap formation happens gradually over several Earth years as winter temperatures persist in polar regions. Atmospheric methane condenses and freezes onto surface materials, building up layers of organic ice that can reach several meters thick in some areas. When seasons change and spring arrives, these methane ice caps gradually sublimate back into the atmosphere. Sublimation means the solid ice transforms directly into gas without becoming liquid first. The ice caps disappear over several years as temperatures warm. Hydrocarbon polar ice caps demonstrate how familiar Earth-like processes operate with completely different materials under alien temperature conditions. The physics of ice cap formation and melting work identically with methane as with water. What happens when Titan's seasons change from winter to spring or summer to fall? The transition periods trigger some of the most violent storms in the solar system. These aren't gentle weather changes. They're massive atmospheric disturbances that can span hemispheres. Seasonal storms occur when atmospheric circulation patterns shift from one direction to another. The changing circulation creates instability that generates enormous methane storm systems. These storms can persist for months and cover areas larger than North America. Storm intensity reaches levels impossible during stable seasonal periods. Rapid atmospheric reorganization releases energy that creates storm systems far more powerful than steady-state weather. Wind speeds increase dramatically. Precipitation rates soar beyond normal levels. Transition storms prove how seasonal boundaries can generate extreme weather events impossible during stable climatic periods. The rapid change between different circulation patterns creates atmospheric violence that exceeds steady-state weather systems. Seasonal changes cause Titan's methane lakes to experience water level changes that make Earth's seasonal lake variations look trivial. Lake levels can rise and fall by dozens of meters as seasonal atmospheric circulation redistributes methane between different regions. During winter, polar lakes receive atmospheric methane transported from warming equatorial regions. Lake levels rise dramatically as more methane condenses and precipitates in cold polar areas. Some lakes double or triple their surface area during winter methane accumulation. During summer, polar lakes lose methane through evaporation as temperatures warm. Lake levels drop dramatically as methane evaporates back into the atmosphere for transport to cooling regions. Some lakes shrink to small fractions of their winter size. Extreme lake level changes demonstrate how seasonal atmospheric transport can dramatically alter surface geography over timescales of several Earth years. Long seasonal cycles create surface water variations impossible with rapid seasonal changes. Seasonal methane precipitation doesn't just affect lake levels. It changes the color and brightness of Titan's entire landscape. Fresh methane deposits create bright surface patches that contrast with older, darker organic materials accumulated over longer time periods. Areas receiving heavy seasonal methane precipitation develop lighter surface colors as fresh liquid methane covers older surface materials. Areas losing methane through evaporation reveal darker underlying materials as bright methane coatings disappear. These brightness changes create seasonal surface patterns visible from spacecraft orbiting Saturn. Entire regions shift from dark to light or light to dark as seasonal methane deposition patterns change. The surface acts like a giant canvas painted by seasonal weather. Seasonal surface color changes prove how atmospheric processes can alter planetary surface appearance on observable timescales. Titan's changing surface brightness provides visual evidence of seasonal atmospheric redistribution. Titan's atmosphere doesn't maintain constant thickness. It expands and contracts rhythmically over the 29-year seasonal cycle, like a planet breathing slowly through geological time. Temperature changes cause atmospheric gases to expand during warm periods and contract during cold periods. During warm seasons, increased atmospheric temperatures gas molecules to move faster and occupy more space. The atmosphere expands upward and becomes less dense at any given altitude. The total atmospheric height increases by significant amounts. During cold seasons, decreased temperatures cause gas molecules to move more slowly and pack more densely. The atmosphere contracts downward and becomes denser at any given altitude. The total atmospheric height decreases correspondingly. Atmospheric breathing demonstrates how temperature variations can alter the physical structure of entire planetary atmospheres. Long seasonal cycles allow atmospheric expansion and contraction to reach equilibrium states impossible with rapid temperature changes. Seasonal temperature and sunlight variations don't just affect weather. They control the speed of chemical reactions throughout Titan's entire atmospheric chemistry system. Reaction rates speed up during warm, bright seasons and slow down during cold, dark seasons. Higher temperatures during summer provide more energy that accelerates molecular collision rates. Chemical reactions that take months to complete during cold seasons happen in days during warm seasons. Photochemical reactions accelerate when increased sunlight provides more energy input. Lower temperatures during winter reduce molecular motion and slow down chemical reaction rates. Some reactions nearly stop completely during the coldest parts of winter seasons. Reduced sunlight also decreases photochemical reaction rates throughout the atmosphere. Seasonal chemistry acceleration and deceleration prove how climate variations can regulate planetary-scale chemical processes. Long seasonal cycles allow chemical systems to reach different steady states during warm and cold periods that would be impossible with rapid seasonal changes. Massive sand dune fields cover Titan's equatorial regions in patterns very similar to Earth's great deserts. These aren't made from weathered rock like Earth's sand. They're composed of organic particles, tiny bits of carbon-rich material that originated from atmospheric chemistry and rained down over millions of years. Wind patterns shape these organic dunes exactly like wind shapes silicate sand on Earth. Titan's dense atmosphere creates powerful winds that pick up organic particles and transport them across vast distances. The particles accumulate in dune fields that stretch for hundreds of kilometers. Cassini radar images revealed dune patterns that mirror the Sahara Desert structure, parallel ridges, crescent-shaped formations, star-shaped intersections where multiple wind patterns converge. The physics of dune formation operates identically with organic particles as with mineral sand. Organic sand dunes prove that familiar desert landscapes can form from completely different materials. The same physical processes that shape Earth's mineral deserts create identical geographical patterns using carbon-based particles on an alien world. Asteroid impacts rarely reach Titan's surface because the Moon's incredibly thick atmosphere burns up most space debris before it can hit the ground. This atmospheric protection means the few impact craters that do exist can remain preserved for millions of years without getting destroyed by additional impacts. Earth experiences thousands of meteor strikes every year that create small craters. Titan's dense atmosphere prevents almost all small impacts and only allows the largest asteroids to reach the surface. Those rare impacts create craters that can last much longer than Earth's constantly refreshed impact sites. The preserved craters provide a record of Titan's impact history spanning geological timescales. Scientists count crater densities to estimate surface ages. Regions with many craters are older. Regions with few craters are younger. Crater preservation demonstrates how atmospheric thickness can protect planetary surfaces from space bombardment. Titan's atmospheric shield created conditions where impact features survive long enough to become permanent landscape elements. Mountain building on Titan creates peaks that rival Earth's major mountain ranges despite being constructed from materials completely different from terrestrial mountains. These mountains consist of water ice that behaves like solid rock under Titan's extremely cold temperatures. At -290 degrees Fahrenheit, water ice becomes as hard and durable as granite. This frozen water ice can support enormous geological stresses and form massive mountain structures that persist for millions of years. The ice mountains experience the same tectonic forces that build rock mountains on Earth. Some mountain ranges on Titan reach heights of several thousand meters above the surrounding terrain. These ice peaks formed through the same geological processes that create Earth's mountains: compression, uplift, and folding of crustal materials under tectonic stress. Ice mountains prove that familiar geological processes can operate with any solid material that maintains structural integrity. The physics of mountain building depends on material strength, not specific chemical composition. Flowing liquid methane has carved river valleys across Titan's surface that replicate many erosion features found on Earth. Meandering channels wend through landscapes like earthly rivers. Tributary systems branch and merge like terrestrial watersheds. Canyon systems cut deep gorges through surface materials. The erosion operates through identical physical processes that shape Earth's river systems. Flowing liquid picks up sediment particles. Transport moves materials downstream. Deposition builds up sedimentary features where flow velocities decrease. Titan's methane rivers follow the same erosion physics as Earth's water rivers. Some valley systems on Titan extend for hundreds of kilometers and display the same dendritic, that's tree-like branching, patterns characteristic of Earth's major river basins. The networks demonstrate consistent erosion patterns, despite using methane instead of water as the eroding fluid. Methane valley systems prove that erosional landscapes depend on fluid dynamics rather than specific liquid chemistry. Any flowing liquid can carve familiar river valley patterns given sufficient time and appropriate surface materials. Broad plains cover extensive areas of Titan's surface, where millions of years of organic particle deposition created some of the flattest landscapes in the solar system. These plains formed as atmospheric chemistry products, gradually accumulated and leveled surface irregularities with carbon-rich sediments. The organic plains contain layered deposits that record Titan's atmospheric chemistry history. Different layers represent different time periods when atmospheric conditions produce different types of organic compounds. The plains function like geological history books written in carbon chemistry. Surface materials in these plains consist almost entirely of organic compounds that would burn like coal if exposed to Earth's oxygen-rich atmosphere. Titan's plains represent the largest concentrations of organic carbon found anywhere outside Earth's biosphere. Organic plains demonstrate how atmospheric processes can create large-scale surface features through gradual material deposition. Long-term atmospheric chemistry can build geographical features that rival geological processes in their landscape-shaping power. Titan's hydrocarbon sea coastlines exhibit all the geographical complexity found along Earth's ocean shores. Wave erosion carves bays and inlets. Resistant materials form peninsulas and headlands. Isolated high areas become islands surrounded by liquid methane. Coastal erosion processes operate identically with liquid methane as with liquid water. Waves break against shorelines and gradually wear away surface materials. Softer materials erode faster and form bays. Harder materials resist erosion and remain as peninsulas extending into the seas. Some coastal areas display features identical to Earth's most dramatic shorelines. Fjord-like inlets cut deep into the terrain. Rocky headlands jut into the seas. Island chains dot the offshore areas where wave erosion has isolated high ground. Hydrocarbon coastlines prove that wave erosion creates similar geographical patterns regardless of liquid composition. The mechanical energy of breaking waves shapes coastlines through universal physical processes that operate with any liquid. Subsurface methane flow creates underground cave systems by dissolving soluble materials beneath Titan's surface. Flowing liquid methane acts like underground rivers that gradually enlarge natural fractures and weak zones in subsurface materials. Cave formation occurs through the same speleogenesis processes. That's cave-forming chemistry that create limestone caverns on Earth. Flowing liquid dissolves materials along underground flow paths. Gradually enlarging passages eventually form caves large enough to create significant underground networks. Some underground networks connect distant surface features through subsurface flow systems that span hundreds of kilometers. Underground methane rivers transport material between surface locations through hidden cave systems that remain invisible from orbital observations. Subsurface cave formation demonstrates how underground fluid flow can create hidden geographical features that significantly influence surface hydrology. Underground cave networks prove that familiar karst processes, that's landscape formation through chemical dissolution, operate with hydrocarbon chemistry. Volcanic activity on Titan doesn't involve molten rock like Earth's volcanoes. Instead, cryovolcanism, that's cold volcanic activity, occurs when mixtures of water and ammonia erupt from subsurface reservoirs. These eruptions stay liquid because ammonia acts like antifreeze that prevents water from freezing solid. Cryovolcanic eruptions create the same types of volcanic landforms found on Earth. Cone-shaped volcanic mountains. Flow features where liquid spreads across the surface. Caldera-like collapse features where subsurface reservoirs empty. The water-ammonia mixtures behave like lava flows despite remaining much colder than Earth's molten rock eruptions. These cold lavas flow across the surface and gradually freeze into solid deposits that build volcanic landforms over geological time periods. Cryovolcanism proves that volcanic processes don't require molten rock temperatures. Any fluid that can remain liquid under local conditions can create volcanic landforms through eruption and flow processes. Long-term weathering processes have carved dramatic erosional landscapes across Titan's surface through millions of years of continuous wind and rain action. Methane precipitation and organic particle-laden winds gradually wear away surface materials to create canyons, cliffs, and badland formations. Weathering operates through the same mechanical and chemical processes that shape Earth's landscapes. Wind abrasion gradually wears down exposed surfaces. Chemical dissolution slowly dissolves soluble materials. Freeze those cycles, where methane alternates between liquid and solid. Fracture surface materials. Some erosional features on Titan display the same dramatic relief found in Earth's most spectacular eroded landscapes. Deep canyons cut through surface materials. Cliff faces expose geological layers. Badland formations create intricate networks of erosional channels. Erosional landscapes prove that weathering processes create similar geographical features regardless of the specific agents involved. Wind, precipitation, and chemical dissolution shape landscapes through universal physical processes that operate in any environment with surface exposure. Titan's surface contains extensive sedimentary deposits that preserve a detailed record of the Moon's environmental history. Different sedimentary layers represent different time periods when varying atmospheric conditions produce different types of surface deposition. Organic sediments dominate most layered deposits because atmospheric chemistry continuously produces organic particles that rain down onto the surface. Seasonal variations create cyclical patterns in sediment composition. Climate changes produce distinctive marker layers that help scientists correlate deposits across different regions. Some sedimentary sequences extend for hundreds of meters in thickness and represent millions of years of continuous deposition. These deposits contain one of the most complete environmental records available for any extraterrestrial world. Sedimentary preservation demonstrates how surface processes can create permanent geological records of planetary environmental conditions. Titan's layered deposits function as natural libraries that preserve information about atmospheric chemistry, climate, and surface processes spanning geological timescales. Life on Earth requires liquid water for every biological process. But what if life could evolve using completely different chemistry? Some scientists propose that hypothetical organisms might use liquid methane as their life-supporting fluid instead of water. This methane-based biochemistry would operate at temperatures that instantly kill any Earth organism. Instead of carbon-oxygen chemistry that dominates terrestrial life, methane life might use carbon-hydrogen chemistry. Cell membranes could form from different molecules that stay flexible in extreme cold. Theoretical methane-based life would breathe hydrogen instead of oxygen. It would exhale methane instead of carbon dioxide. Its metabolism would run chemical reactions that generate energy from completely different molecular fuel sources. Methane biochemistry remains purely theoretical, but Titan provides the perfect laboratory to test whether alternative life chemistry could actually work. If life can use methane instead of water, Titan offers ideal conditions for such organisms to evolve and thrive. Does Titan have the right ingredients for life? Absolutely. The Moon contains abundant carbon in methane and complex organic compounds. Hydrogen exists throughout the atmosphere and on the surface. Nitrogen makes up the majority of Titan's thick atmosphere. Energy sources abound on Titan through multiple pathways. Chemical energy comes from reactions between organic compounds. Solar energy drives atmospheric chemistry that creates complex molecules. Even small amounts of radioactive decay provide energy sources for potential biochemical processes. The combination creates conditions similar to early Earth before life began. All the essential elements exist in abundance. Energy sources can drive chemical reactions. Complex organic molecules provide building blocks for potential biological systems. Titan's chemical inventory demonstrates that the basic requirements for life exist beyond Earth. The Moon shows that other worlds can accumulate the same essential ingredients that contributed to life's emergence on our planet. Scientists have found some of the most complex organic molecules in the solar system on Titan, outside Earth. These compounds formed naturally through atmospheric chemistry without requiring any living organisms. Some molecules approach the complexity of compounds associated with probiotic chemistry on Earth. Titan's atmosphere produces organic building blocks that can lead toward amino acids. Those are the components life uses to build proteins. It also creates hydrocarbon chains that rival the complexity of biological lipids. Those are the molecules that form cell membranes. Some atmospheric products contain chemical features also found in molecules important to Earth's genetic material. The complexity reaches remarkable levels through purely chemical processes operating over geological timescales. No life required. Pre-existing complex organic molecules provide a head start for any potential life that might emerge on Titan. The basic chemical building blocks already exist, ready to be organized into biological systems if the right conditions develop. Unlike most moons that experience deadly radiation and extreme temperature variations, Titan enjoys protection from space hazards that would kill most life forms. The Moon's incredibly thick atmosphere blocks harmful cosmic radiation and creates stable surface conditions. Atmospheric shielding reduces radiation levels to amounts would not immediately sterilize potential life forms. The dense atmospheric blanket also prevents rapid temperature changes that could disrupt delicate biochemical processes. Climate stability means environmental conditions remain consistent for millions of years. Potential life forms would not face the rapid environmental changes that could prevent biological evolution from getting established. Protected and stable conditions show that Titan offers environmental advantages that most worlds lack. The combination of radiation shielding and climate stability creates conditions favorable for the long-term development of potential biological systems. Titan offers not one but two distinct liquid environments where different types of life might evolve. Surface methane lakes provide hydrocarbon-based liquid environments. Underground water oceans provide aqueous environments similar to Earth's oceans. Surface methane lakes could support hypothetical life forms that use hydrocarbon chemistry. These organisms would breathe hydrogen and metabolize organic compounds abundant in Titan's methane seas. They would represent completely alien biochemistry unlike anything on Earth. Underground water oceans might support life forms more similar to Earth organisms. These subsurface seas contain liquid water mixed with ammonia that helps prevent freezing. Earth-like life could potentially survive in these hidden aqueous environments. Dual habitat systems mean Titan could potentially host two completely independent biospheres, using different chemistry. One world might support both methane-based life and water-based life in completely separate environments. The same kinds of chemical processes that may have led to life on early Earth seem to be happening on Titan today. Simple molecules gradually combine into more complex compounds. Organic chemistry increases in sophistication over time. Chemical evolution proceeds toward increasing molecular complexity. Titan's atmospheric chemistry continuously builds more complex organic molecules from simple starting materials. This represents the same type of chemical evolution that scientists think may have preceded biological evolution on Earth billions of years ago. The chemical evolution may proceed along a different path than it did on early Earth, because Titan's atmosphere provides a different energy environment for organic synthesis reactions. Active chemical evolution demonstrates that Titan represents a natural experiment in prebiological chemistry. The Moon shows how chemical processes can lead toward increasing complexity that might eventually cross the threshold into actual biological systems. How will scientists search for life on Titan? NASA has planned one of the most ambitious life detection missions ever attempted. Dragonfly will send a nuclear-powered flying robot to explore dozens of locations across Titan's surface after its arrival in Titan 34. The helicopter-like craft will fly between different landing sites to search for chemical signatures of life. It will analyze soil samples, atmospheric chemistry, and surface materials for organic compounds that might indicate biological processes. Dragonfly's nuclear power source will allow it to operate through Titan's long dark seasons when solar energy becomes insufficient. The mission will continue for several Earth years, visiting locations that represent different potential habitats. Flying exploration capabilities will allow comprehensive life detection surveys impossible with stationary landers. Dragonfly represents the first serious attempt to search for signs of life and prebiotic chemistry across many Titan environments. Scientists are designing even more ambitious missions to explore Titan's methane lakes using boats and submarines. These floating vehicles would search directly in the hydrocarbon seas where methane-based life forms might swim and reproduce. Submarine missions would dive beneath the surface of methane seas to search for life in the liquid depths. Floating laboratory ships would analyze lake chemistry and search for organic signatures that might indicate biological processes. Direct lake exploration offers the best chance to discover methane-based life if it exists. Any swimming organisms would be most easily detected through direct observation and sampling of their liquid habitat. Aquatic exploration missions show that scientists are serious about testing the methane life hypothesis. Future missions could search more directly for alternative biochemistry on Titan. The ultimate goal involves bringing Titan's organic materials back to Earth for analysis in the world's most sophisticated laboratories. Sample return missions would collect soil, atmospheric particles, and liquid samples for detailed study using equipment impossible to send to Titan. Earth-based laboratories could analyze Titan samples using techniques that require massive instruments. Advanced mass spectrometers could identify organic compounds with unprecedented precision. Biological assays could test whether Titan materials show any signs of past or present life. Sample return missions would take decades to complete due to the enormous distances involved. But the scientific payoff could revolutionize our understanding of life's possibilities throughout the universe. Bringing alien organic chemistry back to Earth represents the most definitive way to answer questions about life beyond our planet. Sample analysis could provide evidence that settles the question of whether life exists on Titan. What would finding life on Titan mean for science? Such a discovery would represent the most important biological breakthrough in human history. It would prove that life is not limited to Earth-like chemistry and can evolve using radically different biochemical systems. Titan life would demonstrate that biology may reflect universal principles rather than Earth-specific accidents. Life might be far more common throughout the universe than scientists currently believe, if it can use multiple different chemical foundations. The discovery would also provide insights into life's origins on Earth. Studying alternative biochemistry would help scientists understand which aspects of biology are universal and which are unique to terrestrial life. Revolutionary implications would extend beyond biology into philosophy and humanity's place in the universe. Finding alien life using different chemistry would confirm that Earth does not represent the only possible approach to creating living systems in the cosmos.